Okay, let's continue to the reaction of ethers. Ethers, as by their nature, they are not very reactive. That means the number of reactions that ethers would undergo is limited. Ethers, as you know, have a very neutral structure. Here you have the only reactive species on the ether functional group is the oxygen lone pairs. So those lone pair of oxygen act as a basis. So in the presence of a strong acid like HBr, HI, HI, hydroiodic acid, hydrobromic acid, the ethers could get protonated. So in general scheme, I just put here the proton, which is a strong acid, would protonate always the ether oxygen. So this protonated oxygen ether then would undergo a nucleophilic attack by the counter anion at the carbon center to make a carbon halide bond. This is carbon halide bond, and the rest of it is acting as a leaving group. So it would be an alcohol. So the leaving group in this case is the alcohol, a neutral alcohol, because pair of electrons would neutralize this positive charge. So it's not very diverse set of reaction in ethers. In ethers, you always need to think of protonating the oxygen, because those lone pair of electrons act as a base. They are available for abstracting a proton. Therefore, they are the center of the reaction. So ethers as functional group are not very reactive, and you don't see so many reactions with ethers. So to demonstrate the above scheme, I have here a Tert-butyl methyl ether, T-butyl methyl ether, TBME. It is called actually TBME. What it means is Tert-butyl methyl ether. So TBME, when it's treated with hydroiodic acid, the first thing is, as I said, it would get protonate the oxygen. So what we get would be oxygen that is protonated because it is bound now to a proton plus. That's what we get. After protonation, now we have two possibilities. So one important point you need to remember in ether reaction is after protonation, which one would be attacked by a nucleophile, or which one remain as a carbocation to do SN1 or SN2. So this is very important distinction. For example, in this case, there is a possibility this could make a tertiary cation by just giving this intermediate, because you can just easily donate that pair of electrons and forms a carbocation. So depending upon what kind of ether you are dealing, it could be as SN1 or SN2. So now the leaving group is methanol, of course, CH3OH has been produced. Now the I minus, the counter ion, the nucleophile, would attack this and produces CH3, Ci alkyl halide, a tertiary alkyl halide, would be formed in methanol overall. So that's what happens. So this mechanism is SN1. But if it goes through SN2, for example, another example, when you have dimethyl ether, you could protonate this just the same way we protonate that. CH3O, CH3, actually this is protonated now, a plus. Now, at this point, the I minus is still around. Now, you cannot form a carbocation on this because a carbocation on metal is very unstable. There is no metal carbocation. So this would be just the I minus would attack this. When this attacks, this one would be a leaving group. So now you would create metal iodide from the attack with this and methanol. So it's a minor distinction. This is going through SN2 because you don't form a carbocation. So this is some details in the mechanism of the reaction you need to remember. We have also here a metal benzene ether. It's a phenyl ether, phenyl metal ether. So it's phenyl metal ether. So we are protonating with a strong acid, initial protonation. This would abstract that. So the protonation is actually happening by the oxygen lone pair of electrons picking up a proton, the positive. That's how it goes. So the arrows are, these are the way they should be indicated. So now you have H here, a plus, and CH3, still a pair of electrons, because there are two lone pair of electrons. Now in this case, the Br can only do SN2 on this metal group. There is no SN2 on sp2 carbon. If you remember our discussion for SN1, SN2, SN1, SN2 can happen only on sp3 carbon. So there is no, the Br cannot come here and attack here. Rather, it would only form, attacking this, you would have a product which looks like a phenol, OH, plus methyl bromide. So these are, mostly the reaction of ether is very limited. It's initial protonation of the oxygen. That's what you need generally remember. And then after that, whatever nucleophile is around, it can do an SN1 type, or if it is forming a tertiary kind of carbocation, that's okay, that's fine. It goes through SN1. But if it's not forming, if it cannot form the alkyl group, it can only form, can have only the leaving group, then you'd perform SN2. So this is also SN2. So remember to distinguish this also as whether it goes through SN1 or SN2. It is based on the substrate or the R group that's present on the ether group. So ethers in general, they do protonation, or they get protonated by strong acid, not by a base. By base they don't react with the base because they are already, even though they are neutral, the lone pair of oxygen, the lone pairs on oxygen act as bases that could abstract a proton. So the reaction is with a strong acid. So if you treat any ether with a strong acid, it would start to decompose into two type groups. Based on what you have, it will be always an alcohol and an alkyl halide. If you remember here, you have an alkyl halide group product here and an alcohol. Here also an alkyl halide and an alcohol. Here an alcohol and alkyl halide. So if you just treat with some kind of hydroiodic, hydrobromic, hydrochloric acid, you'd form the alkyl halide and also an alcohol. So this is a summary for what ethers do in the reaction. It's not very wide range of reactions that ethers can do. The next one would be we'll be just looking at the reaction of epoxides. Okay, let's continue with reactions of the three functional groups, alcohol, ethers, and epoxide. As you know, we have already covered alcohols, ethers. Now we're going to just focus on epoxides. From a structural point of view, epoxides are highly strained structures. That makes them very reactive. So epoxides, as you see, are a three-ring system bridged by oxygen. That makes them, there is an angle strain that would prevent them, that makes them very strained and react very promptly, or they are very reactive species. Electronic structure of epoxides, you can only see also, this is a polar bond, polarized bond, where a lot of sigma negative is on this oxygen, and the carbons are relatively positive, sigma plus, sigma plus. That's where the reactivity center is. So if you just look at here, this carbon is relatively positive, this is positive as well, but the oxygen is relatively more negative. So due to the fact that there is angle strain, epoxides are very reactive. Epoxides are reactive because of the strain. They tend to open the ring system. So the reaction is ring opening of the epoxide. So they react in two conditions. One is just in a basic or neutral condition where you have only a strong nucleophile, or in the second condition in the acidic condition as well. So the fact that they would react in the nucleophile is because this is a positive center. This is a positive center, so the nucleophile can come and attack that carbon. Or the fact that this is highly electron-rich oxygen, it is a very strong Lewis base. That means it can attract, gets protonated by an acid. Once it is protonated, it would be tri-coordinated, and with a plus charge, that would become very prone to the ring opening to neutralize that charge. So I'll show you both. So a nucleophile, necessarily with pair of electrons, would come in, attack one of the carbons, and this opens into the opposite direction. So what you would get is you have O minus with a pair of electrons. It opens with this pair, and a nucleophile now attached here on this carbon, right? So you have a nucleophile that's attached, and the ring system would open. So that is one of the nucleophilic attack on epoxides. So epoxides reaction is always ring opening. They ring open either in a nucleophilic condition, meaning basic condition, or in acidic condition. Both are just opening of the ring. So one is you have that, if you just treat this with additional water or something like that, this would get the hydrogen from this, and you have a neutral alcohol molecule. So you have OH here, and nucleophile. So that is a neutral molecule now. So epoxides can be converted into alcohol to the corresponding alcohol by just opening it with a nucleophile and treat it with water or any other acid. In the second mechanism, you have a loose base here, picks up that proton, it gets activated. Now a plus, because it donates. So now, if you just see, this system is now intermediate. It's not a neutral species, it's very active, so the ring can just easily open by any nucleophile in the system. For example, if you have an X minus, let's say you have an acid HX. Let's say this was an acid HX. Now, once it gets protonated, the X minus, the negative charge on the acid, would now act as a nucleophile. It attacks either here or there. We'll discuss which side is preferable. Now the ring opens like this. Now you are creating this molecule. OH is opened. Now you have X minus here. So this is what you get. So the alcohol is generated. Here also an alcohol is generated. So actually, epoxide ring opening and make an alcohol is a common way of making a secondary alcohol. So these are the two mechanisms. One is a nucleophilic or basic system. The second mechanism is in an acidic condition. So to just show you an example of these two, for example, if I have this epoxide, let's say I am assuming these are hydrogens, okay? So I have very easy epoxide. Let's treat with a nucleophile, cyanonucleophile, a strong nucleophile, cyanide. And that's step one. Step two, we'll treat it with water. Just exactly what I have here, step one, step two here. So that is what it means. So the cyano group can attack with a pair of electrons this carbon. This opens up, then it picks up on the O minus, it will open up and takes up a proton. So what we have created is an OH here, two hydrogens right there, two hydrogens are still there, and the cyano group is here. So that's what we have created. Cyano comes in, epoxide opens. Or in the second mechanism, for example, if I have here this epoxide, and if I treat this with hydrochloric acid, so if you just treat an epoxide with a hydrochloric acid, the initial step is the protonation of that oxygen to become very active intermediate, like this. These are hydrogens. These are hydrogens. Hydrogen, hydrogen, hydrogen. So the Cl minus, which is acting as a nucleophile now, like I said here in the X minus, this would attack this carbon. This opens up. Now we form a chlorohydrin compound. Chlorine, H, H, OH is formed there, and the two hydrogens are still there. So that's a chlorohydrin actually. So this is the cyanohydrins. So the main reaction now, a point to take for you is whenever you see an epoxide, the main reaction is the ring opening. The ring can open under basic condition or acidic condition. But both needs a nucleophile that would open the ring system. So the acid mechanism is activating the loose base. In the nucleophile, if it's a very strong nucleophile, it just kicks on the carbon, which is positive, and that's the ring opening. So the main known nucleophiles against epoxide opening are hydroxide is one, cyano is one, cyanide, alkoxides like OHs are alkoxides. These are strong nucleophiles. Sulfides, alkyl sulfides, for example, methyl sulfide would be a nucleophile. Ammonia can open also as a nucleophile using those. These are strong nucleophiles, strong nucleophiles that can open the ring system like that. So a nucleophilic, these are examples of a nucleophile that can attack the epoxide and cause ring opening. So we'll continue with more specific examples of epoxide ring opening. So the reaction in general is epoxide ring opening reaction. So you should be familiar with the terminology reactions. So whenever you see an epoxide, a three-member ring, because of high angle strain, the epoxide is prone to ring opening. So that ring opening can be through a basic or nucleophilic condition or an acidic condition where the acid activates that oxygen to be open, to be labile by attack with any weak nucleophile. Okay, we'll continue more with specific examples of epoxide ring. Okay, let's continue with more of examples of ring opening of epoxide reactions. There are some important points you need to remember during epoxide ring opening. First of all, the nature of the epoxide is important. This epoxide, for example, has hydrogens in both sides. So this is a symmetrical epoxide. That means groups that are in the left and right are the same. In that case, obviously, the epoxide is symmetric, so the ring opening can happen from any of the two carbons. So these carbons, which are the sigma plus, the sigma negative here, and during the symmetrical epoxide, it doesn't really matter which side the nucleophile comes. But when it comes to unsymmetrical epoxide, like here, in the right side, if you see two hydrogens, the left side has more bulkier groups, CH3, CH3. So those are larger in size than the other side. So there is preference which direction the nucleophile comes in. In unsymmetrical nucleophiles, always the nucleophile comes under this condition, meaning that nucleophile ring opening, not acidic one. The acidic is the reverse, but this is just a nucleophilic opening of the ring happens from less substituted carbon side. That means if we take this example, this is unsymmetrical epoxide, the ring opening by this metal sulfide nucleophile will not attack on this carbon. The nucleophile comes and attacks this carbon. So there is a preference to attack this carbon because of sterics. There is steric crowding here, so the nucleophile first actually comes in onto this carbon, not this carbon. So ring opening of epoxide by a nucleophile in unsymmetrical case would be like this. So that would be OH after water is added to that O minus. Remember what I already showed you in the previous session. So this CH3 would be here, but the S, the carbon, which has the hydrogen here, and the nucleophile comes in here, that is SCH3. Of course, there is a hydrogen there. So this is a nucleophile coming in on this carbon, not the other carbon. So this is ring opening by a nucleophile. Always remember less substituted carbon. Nucleophile is at the less substituted carbon. This is when a nucleophile is used. Again, you need to remember that. We'll see another example. Actually, I just want to give you that example right now. That example could be the same. Let's do the same thing, but in acidic condition. So you have this. I have CH3 here, CH3, but here are hydrogens, unsymmetrical, they are not the same. But in this condition, sulfuric acid and water is used. So how is the nucleophile comes in? In this case, the nucleophile would be water. So the initial step, if you remember, is a protonation by H plus, in quotation. That's what sulfuric acid gives us. So what we generate would be, as an intermediate, I'll go stepwise, CH3, CH3, protonation, activation, that means H, H. In this case, since this is acidic ring opening, the nucleophile doesn't come to less substituted. The nucleophile, which is water, would come to the more substituted. So what you get would be, overall, what we would have would be H. I will just use this. This OH is from the CH3, CH3, OH comes on this carbon, and OH is here. So it's a diol, actually. That's what we form when epoxide is opened in the presence of acid and water. You get a diol. One alcohol from water, one was from the epoxide itself. So this is one OH, the other is from water. So a diol is formed. Diol is a two hydroxys in the same compound. A 1,2-diol is formed. A diol is formed by ring oxygen opening by an acidic condition. For a basic or nucleophilic condition, you open from a less substituted side. In the acidic condition, you open from a more substituted side. So this actually came as a nucleophile from water. So ring opening happens like this. The OH comes in, the ring opens this. So this is the epoxide's OH, but this is the nucleophile. So the nucleophile is right here. The nucleophile always comes from a more substituted side for an acidic mediated reaction. So remember this, we'll do more problems with this. And also in terms of stereochemistry, sometimes the epoxide ring opening is also ring stereochemical outcome. It should be consistent with the stereochemical outcome. For example, here is the ring opening by a nucleophile, a stronger nucleophile. So the ring opening can happen if the, now here the epoxide, as you see it, is coming towards me. So the ring system is not just flat on the board, it is like this. That's why you have a wedge on it. That's what it means. If I drew, for example, something like this, the epoxide ring is not on the plane, but down into the plane of the board. So here it is coming to us. So the ring opening, this is a symmetrical epoxide. That means it doesn't matter, it would be this one or that one, right? So let's just assume it's coming from here. So the methoxide can come from backside, let's say. If it comes from backside, you could generate it. This is always opening OH. That means it picks up one H from this after it's opened, but the methoxide is coming from the back. But there is nothing that prevents this methoxide coming also from this side. That means it can also create so the mirror image of that would be OH and OCH3. So these are mirror images, right? Actually not mirror images. So I will just leave that. I can just leave this because that shouldn't change. OH and OCH3. So that is, these are not actually mirror images. So if that is the case, this also should be this. So that's how it happens, meaning that when this comes in, that goes to behind. So if this comes from this side, the OH would go the other side. So these are enantiomers. The point is that you can generate enantiomers. That is racemic mixture. So it is optically inactive solution because you have 50-50 of those compounds. So if I just rotate this, this would be a mirror image to the other. So how about if we have sulfuric acid water? So it would create the same thing, but the point is now so it creates the same thing. So, but the mechanism is different, but they are diols. So the point is I have OH here, diol, because sulfuric acid, water, there is no nucleophiles, the nucleophile is water. So here also you would create OH, diol. Those are also enantiomers. So that's how it looks like in terms of ring opening with acid and with a base. Symmetrical and unsymmetrical epoxide. So that's what you need to remember in terms of ring opening by an acidic condition, a basic condition, symmetrical, unsymmetrical epoxides. So with this, we'll conclude with the reactions of epoxide. So in the nutshell, what you need to remember would be epoxide reactions are ring opening. The ring opening can happen through a basic condition, meaning that a nucleophile ring opening, or in acidic condition. In acidic condition, the nucleophile comes from more substituted side, opposite to a nucleophile that comes from less substituted in unsymmetrical nucleophilic mechanism. So these are the distinction. You need to do more exercises to solving problems, and we'll do that in another video. With this, we'll conclude the chapter, and in the next series of videos, I will be solving all problems that are related to this past chapter we have already covered. Okay? Thank you.